So we can also have gases dissolved in water or other liquids. Can of soda pop. Okay, so I grew up in Minnesota and Iowa where we called it pop. And then I went to Indiana where people were a bit more conflicted, but most of them called it soda. And then I lived for 3 years in North Carolina where it was definitely soda. And I come out here and it's soda. And so I've gotten used to calling it soda, but in the book they use both words together, which I guess is supposed to sound dumb to everybody. Could I have a glass of soda pop, please? It just sounds dumb, doesn't it? So I'm just going to call it soda and ignore the word pop and deny my upbringing.
In the South, they call it all Coke. No
Yeah, they do that
just
too.
Coke.
Yeah, I'd like a Pepsi Coke or an Orange Coke or a Dr. Pepper Coke. What kind of Coke do you have? It's crazy.
You sell here.
Well, and then some places, you know, they soft drinks as opposed to hard liquor. And the other thing in the South is the tea, sweet tea or unsweet. It's not sweetened or unsweetened. It's sweet or unsweet. And when it's sweet, it's really, really sweet. And if they don't specify, it's sweet. And you go to, McDonald's and they have both kinds, sweet and unsweet. Yeah, lots of sugar. Lots of sugar. It's like a different parts of the country are like different countries, really. I mean, a lot of people in California, you may have never left California because why would anyone need to leave California, right? Everything's here. But there are some really interesting places in the rest of the country. If you have a chance, you should go there. Okay, so a can of soda is an example of a gas dissolved in water. Most liquids actually do have some gases dissolved in them. How can fish breathe in the aquarium or in the river? It's because there's gases, there is air dissolved in the water. So lake water, seawater, the water in your aquarium, it has dissolved oxygen and other gases from the air. And otherwise the fish couldn't live. Your blood has dissolved gases in it. It's got nitrogen, oxygen, carbon dioxide dissolved in it. And you would die if it didn't. Even tap water has dissolved air in it.
When you say dissolved, does that mean like it's solid or that it's just one atom?
It's in solution. So a solution being a homogeneous mixture means that it's evenly distributed throughout the liquid and it's not part of a compound that has fixed proportions, but the proportions can vary. So you can have a little bit of oxygen or more oxygen, and it's a solution, not a compound. Because there's oxygen in water, but not oxygen gas. It's bonded to hydrogen, and it makes up the water. But this is air, oxygen, nitrogen, carbon dioxide, gases that are dissolved in the water.
I guess I'm just like when we actually use oxygen, like our muscles, is it a liquid then? Or
No, it's a gas dissolved in your blood.
She's dancing around.
yeah, okay.
It's a gas dissolved in your blood.
I'll read the book for that.
So you put sugar in water and you stir it up. Does that mean that the sugar is a liquid now?
No.
No. It's the particles are separated and they're distributed throughout the water. So the oxygen in your blood is individual oxygen molecules separated and spread out in the plasma of your blood. So we said that the solubility of solids increases with increasing temperature. And when, if you have trouble remembering that, think about tea and sugar. So if you are trying to dissolve sugar in a glass of iced tea or a cup of hot tea, which is it going to dissolve more easily in? In the hot tea, right? It's more soluble in the hot tea and it dissolves faster. And in iced tea, man, that's just hard. It's hard to put sugar in tea that already has ice in it. With gases, the solubility decreases as the temperature goes up. So think about a can of soda. If it's warm, the carbon dioxide is going to come out a lot faster than if it's cold.
If we had tea originally and we put a sugar in, obviously it's warm, it'll saturate much easier. It'll dissolve it much easier.
Mm-hmm.
So if we do that and then we cool it, Would we have a supersaturated solution at that point if we put more than would be normally?
If you created a saturated solution in hot tea, which would be a lot of sugar, and then cooled it off, yes, you could have a supersaturated solution. Yeah, I know, you're gonna go home and try it. That's fine. That's something you can definitely go home and try. But sometimes what happens is you don't actually end up with a supersaturated solution, but it was saturated, and as it cools down and the solubility decreases, the extra sugar precipitates out. It'll crystallize out. So if you take a saturated solution that's at a warm temperature and you just let it sit, the sugar will come out, and that's how you make the rock candy. Is the sugar, that extra sugar that's no longer soluble, crystallizes out.
So we have to flash cool it then. I believe we're nitrogen, make sure it's
Flash
cool.
cooling it might work, yeah. And some solutes like sodium acetate will do that without any special messing around. They'll just become supersaturated, which makes them so fun.
What chemical, what did you use?
That was sodium acetate.
Sodium acetate, yeah.
Yep. Yep, sodium acetate. So if you take cold soda and pour it, it fizzes some. But if you take warm soda and pour it, it fizzes up a lot. And that's because the carbon dioxide is less soluble in the warm soda, and so it's much more likely to come out. You also see that if you have, a cup of soda with ice in it that's remaining cold and a cup of soda that's warm, and you just let them sit there open to the atmosphere, they'll both go flat eventually, right? All the fizziness, the carbon dioxide will come out. But which one will go flat faster? The warm one. And that's something you could try at home too if you're willing to waste soda, right? Let it go flat.
So that's the connection with thermal and kinetic energy, right? That the amount of energy in there is causing them to be free, and therefore the bonds are less and they're excited, so they're released.
It is related to the thermal energy. Yeah, and it's the energetics of that is kind of complicated, which is one of the reasons we don't talk about it in this class. But it's interesting. So here's something you can try at home. Put some tap water in a pan on the stove and heat it. And stand there and watch it. It's really not true that a watched pot never boils. But if you watch it, as the water starts to heat up, you'll see little teeny tiny bubbles start coming out. But it's not boiling yet. What's going on? Well, there's dissolved air in the water. And as you heat the water up, it comes out of solution, and you see the little bubbles coming to the top. Then when it finally gets to the boiling point, then you see lots of big bubbles. And so sometimes in lab, you've been heating something, and you come and ask me, is it boiling yet? It's like, no. You got to have those big bubbles, this vigorous boiling. The other stuff is just the air coming out of solution because the solubility decreases. That's why it's important for fish. So an aquarium, if you have fish that are accustomed to a cold temperature, there is more air in the water, there's more oxygen in the water at cooler temperatures. And so if the temperature of the water is warmer, it's not that the fish is getting cooked or anything, it's just that there's not enough oxygen for it to breathe. It's like when we go up to the mountains, high elevation, we're out of breath all the time. It's just not enough oxygen. That's the experience that fish have. And so when you have like big industrial plants that are dumping warm water, thermal pollution, into a river, it can kill the aquatic life because it warms up the river, the oxygen levels go down, and then the plant life and the fish, aquatic life die. The solubility of gases also depends on pressure, and this is called Henry's law. The higher the pressure of a gas above a liquid, the more soluble the gas is in the liquid. So if we have that's not very many. If we have a few gas molecules, then we will have some gas dissolved in the liquid. If we increase the pressure of that gas, if we cause there to be more gas particles in the space above, then more will dissolve. And this has to do with equilibrium. So we have dissolved gases here, and some of that dissolved gas is escaping, but then in the gas state here, they're zinging around, and when they hit the liquid, they can dissolve. And so you have gases dissolving and gases, what would the other word be? Escaping, we'll use that word. So you have an equilibrium. If you increase the pressure of that gas, you increase the rate at which gas is dissolving, because more of these gas molecules are hitting the liquid and getting trapped. It's like condensation, but it isn't condensation, because it's not condensing into a liquid, it's dissolving into a liquid. But you increase the amount of gas that's going into the liquid, and so then you end up increasing the amount of gas that's dissolved. And that's what's happening in a soda bottle or a soda can. It's packaged so that there's pressure of carbon dioxide. Now, if you put pressure of another gas, then that's not going to affect the solubility of the first gas. So if, say, this is carbon dioxide gas, and we put a lot of nitrogen gas up here and increase the pressure of nitrogen, but not the pressure of the carbon dioxide, that's not going to affect the solubility of the carbon dioxide. It would affect the solubility of the nitrogen, but not of the carbon dioxide.
What do we compress then?
Pardon me?
What do we compress to?
If you compress it, then you will be increasing the pressure of that gas that you're interested in,
Well, I mean,
and other
What if
gases.
we include both, like the nitrogen and the carbon dioxide?
If you
and we simply compressed it?
Right. If you include both and compress it, then you are increasing the carbon dioxide concentration, the pressure of carbon dioxide, and so you will increase the dissolved amount.
For both gases, though, right?
For both of them, yeah. But it will be more effective if you only increase the pressure of the carbon dioxide, because the difference will be greater. It's proportional to the difference in the temperature. So when you open a can of soda, there's always a little bit of a headspace in a soda can or a soda bottle. And up here is carbon dioxide under pressure. When you open the can, you release that pressure, and when that pressure is gone, the solubility of carbon dioxide in this soda goes down and it begins to bubble out.